Hi folks, thank you for coming to the third talk of the session about vectorization. Next to me is Vasileios from working at Intel. He's going to talk about supporting variable vector width, and I'm curious about whether it has anything to do with ARM's scalable vector extensions.
All right,
Stage
thanks
is
for the
yours.
introduction. Okay, hi everyone. Thanks for attending my talk. I'm Vasileios. I work at Intel, and this talk is about how we can extend SLP to support variable vector widths, but it's also an introduction to SLP, so I have a lot of things about the existing support of SLP in LLVM. So this is joint work with Rodrigo from Edinburgh and Fabrizio from PUC Minas. All right, so that's my disclaimer. And let's get started by defining what vector width is. So according to Wikipedia, it's a one-dimensional array, so it looks like this. And vector width is actually the vector size. And in the vectorizer jargon, we also use the term vector length or vector factor, so please don't be confused. All of these terms are exactly the same, vector width, vector length, and vector factor. And I'm going to use them interchangeably throughout this presentation. So now that we got this out of the way, I'll talk about SLP. So SLP is LLVM's second vectorizer. And its job is to vectorize straight line code. So SLP is an acronym. It stands for Super World Level Parallelism. And this acronym was introduced in the original SLP paper, and the term has actually caught on. So SLP is different from the loop vectorizer. So it's not vectorizing across iterations, it's actually vectorizing across instructions. So here's an example. So we have this for loop, and this is basically a very simple loop. It copies B to A, so B of I, A of I equals B of I. And this is, think of it as a hand-unrolled version of the loop. So if you give that to the loop vectorizer will try to jam consecutive iterations, and it does so by, first of all, increasing the step, and then widening each and every statement in the loop. So conceptually, that's what the basic loop vectorizer does. It will try to widen everything. So that's why we have, the input will be this A of I equals B of I, and the output will be a widened version. So you see there we have the indexes from the jammed iterations. So we are storing into A of I plus 4, I plus 8, and I plus 12. And it keeps doing the same thing for all the statements. So that's how a basic loop vectorizer works. And SLP is completely different. It doesn't care about the loop. It doesn't even change the loop structure at all. So we still have a step of 4, so no change in the loop. And the SLP will basically try to combine, it will try to collapse all these instructions into a single wider instruction. So it will collapse all these 4 statements into a single statement that reads from B of I to I plus 3 and writes into A of I to I plus 3. So note here that, of course, these are interleaved accesses, so the loop vectorizer can probably do a better job than just this. All right, let's see, is SLP any good? I mean, if you run the loop vectorizer first, is there still opportunities left for SLP? So I ran some tests. I grabbed the top of the trunk from a few weeks back, and I ran some tests on my home machine. And the black bar is basically O3 with just the loop vectorizer enabled, and the orange bar is O3 with loop vectorizer and SLP. So as you can see, there is some difference there. So there are still some there is some parts of the code that don't get vectorized with the current loop vectorizer. All right, so I'll now I'll try to introduce SLP. So I'm going to use this code for the next couple of slides. And I'm going to try to explain the details, like what it does and how it works. So this code can be represented by these DAGs. So there's a one-to-one correspondence between the DAGs and the code. And these DAGs are basically the use-def chains. So SLP actually works on these DAGs, so that's why we need them. So on the bottom half of the slide, I'm going to talk about I'm going to show the SLP graph, which is the main data structure that SLP is using. And I'll show how SLP is actually building this graph. So the first thing that SLP does is that it starts from these store instructions. So we have these stores to consecutive memory addresses. And SLP will group these stores together, and it will form the first node, which will become the root of the SLP graph. So next, it will go through the definitions, and we'll try to group them together, and it can do so. So there are like 4 subtractions that can be combined together. And then now we have these. We have 2 operands. We have the left-hand side operand and the right-hand side operand. So SLP will go to the left-hand side first, and now we have memory accesses which are not consecutive. So SLP will basically just stop here, and it will mark this as a gather instruction. Then it will move to the right-hand side, and we have a similar story. So we have 2 bitwise ends, 2 loads. So SLP will basically stop. So the existing strategy right now is after we run the cost model, and the cost model will tell us that this is not profitable to vectorize, the strategy of the SLP in LLVM is basically to reduce the vector factor. So we go from vector factor 4 down to vector factor 2, and we retry. So we grab a pair of these seed instructions. We get the first 2 stores, basically, and repeat the process. So we form the root node of the DAG. Then we try to combine the subtractions. Then we go to the left-hand side. But as you can see here, now we have these 2 loads that can be combined together. And same story for the other side. So we have these bitwise operations that can be combined all the way up to the loads. So if we run the cost model, SLP says that, yeah, this is profitable, so that gets vectorized. And now we have 2 more stores to work with, so still at a vector factor of 2. And we basically do exactly the same process. So we build the SLP graph, we run the cost model, and we check. And SLP tells us, yes, go ahead and vectorize it. All right, so now that I gave you an overview of what it does, so let me go through a bit more details about the actual algorithm. So the input to SLP is the scalar IR. Then the first thing it does is it scans the code and looks for seed instructions. So seeds are usually either stores to consecutive memory addresses. They can be like top of reduction trees, and many others. Then it groups them into chains. So it forms these seeds. It rearranges them into chains. And each chain is basically, like for example here, a chain would correspond, all these stores would correspond to the same chain because they're using the same base pointer. And then after we form these chains, then we initialize the vector factor. So the vector factor is now 4 because we have a data type which is 64 bits, and we have a 256-bit vector architecture. So yeah, we take into account both the data type and the target architecture to initialize the vector factor. And now so since we have these chains, we grab a 4-wide group from the chain and basically start the SLP process. So we ask SLP to build the SLP graph, as I showed you earlier, and then we calculate the cost. Then we check whether the cost is profitable. And then if it is, then we generate code. And we also, if there are any gathers, we push them back into the seeds, which actually helps us do some sort of variable width SLP support, but it's kind of an afterthought, actually. So it's not very powerful as the one that I'm going to present. So finally, these seeds that we managed to vectorize get removed from the seed chain, and the process repeats. So in the other case where the vector factor, if the SLP graph is not profitable to vectorize, then we check whether we can reduce the vector factor. And if we can, then we divide it by half, and then we repeat the process. So as I showed you earlier, we'll reduce the vector factor down to 2, and we'll grab the 2 seeds, vectorize them if possible, and grab the remaining seeds and try to vectorize them. So the process repeats until there are no seeds left, basically. All right. So here's why we need variable width SLP. So I'm going to use the same code, and I'm going to show you how this new scheme can perform a bit better. All right, so once again, we start with a vector factor of 4. Then we create another node out of the 4 subtractions. And now we reach the point where SLP bailed out. As you can see, of course, these 2 loads can actually be combined together. And that's exactly what we do. So we emit a shuffle instruction, and we reduce the vector width from 4 to 2, and that allows us to keep on vectorizing. So we do the same thing for both operands, and same thing on the other hand, on the other side. So we have bitwise ends and loads, and the only way to combine them is through a shuffle. So by reducing the vector width while building the SLP graph, we can actually vectorize this code completely. So if you run the cost model, it tells us this is profitable, and yeah, that's actually vectorized, and it performs a bit better than the previous code because it contains a few wider instructions. All right, so we're already introducing shuffles, so why not try some permutations? So I changed the code a bit, so this is a slightly different example, but I'll show you what I mean by that. So if you give this code to vanilla SLP, it will stop at more or less the same point with vector factor 4. Then when it falls back to vector factor 2, it cannot fully vectorize the code because you have instructions that cannot be combined, like the bitwise end and the loads. So this is where variable width support can help us, and along with permutations. So we follow the same process as before, so the left-hand side is exactly the same, but the interesting part is on the right-hand side. So we have these bitwise ends that can be combined together with a vector factor of 2, but these loads are consecutive, but they're in the wrong order, so they have to be swapped. And actually, we're lucky enough that both of them need to be swapped. So we can actually have a shuffle instruction that performs a permutation of this code. And the same thing happens for the other side. The loads have to be swapped, and we do that within this shuffle. So we run the cost model, and that's much faster code than what vanilla SLP can actually do right now. All right. So far, I've talked about how we can reduce the vector width and how this can help. And I'm going to talk about how making it wider can actually help also. So this is a totally different example. We form a vector factor. We can only build an SLP graph with a vector factor of 2, since we just have 2 stores at the moment. So vanilla SLP will build the graph fine until the loads, and the loads are non-consecutive, and therefore we cannot, it will basically stop at this point. So if you run the cost model, it doesn't get vectorized. So let's see what happens if we can widen the graph. So SLP, the variable with the variable width support, it will still build it will basically build the same graph until the subtraction. And then we check the operands, and we see, oh, we have 4 bitwise end operations. So maybe if we're lucky enough, we can start vectorizing 4 wide from that point on. And that's exactly what we're doing. So we're trying it out. We're widening the vector from 2 to 4, and now everything gets magically vectorized. Well, obviously, this is an artificial example, but we did see a few cases where this actually happened in practice. All right. So I'll now talk a bit about the implementation. So I'll try to be a bit brief because I don't want to bore you to death with all the actual function names and stuff. So we modified the build tree recursive function to handle the variable width. And the way we do this exploration is that we are spawning localized build tree rec searches using new seeds, basically. So in order to decide whether we should do shortening, widening, or permutations or anything in between, we are calling build tree rec with a capped depth. So we're going to explore it only for like a depth of 2 or 3. And then we evaluate these subtrees using the existing TTI support, and we basically pick the best. So in order for this to work, we had to make some changes in the scheduler. So if you try this right now, the scheduler will complain. Well, it will actually fail because it will say that some instructions have already been scheduled and stuff. So we had to implement a rollback and replay mechanism in the scheduler of the SLP pass. And yeah, and obviously we had to make some changes in the code generator to support the variable width and all the creation of the shuffle instructions. All right, so here's some performance numbers. So please note this is with the loop vectorizer disabled. So it's basically just SLP compared to SLP with the variable width support. And we have also enabled these horizontal stores flag. And I mean, we see that there are some cases where this actually helps. To conclude, I presented an introduction to SLP. I talked about how the existing SLP support works in LLVM. And I also presented how we can extend it with support for variable vector width. And I showed you that we can build a more effective SLP graph, and it can increase performance. And what I didn't talk about is that the compilation time increase is not very big. So the only overhead here is the localized searches using build tree. And you can always cap it as much as we want. So yeah, so it's not the overhead is not great. And finally, all these changes are localized to the SLP Vectorizer, and it doesn't need a complete redesign of the code. And so this is like a non-intrusive way of achieving the variable vector width. So that concludes my talk. So I'll be happy to take questions, and thank you for your attention.
Thank you, Vasileios. Who has questions?
Hi. You showed how you get different costs out of different combinations of the way that you're calculating these. Is the direction of that predictable enough that you can count on the first one you find that looks beneficial being the best, or do you do something to consider of the possible things that you could do which will be the most beneficial?
So are you talking about, are you referring to the comparing like what vanilla LLVM does versus when we support variable width, or are you talking about?
Yeah, so like here on the left,
Yeah.
you did the cost modeling and you said not vectorized because cost is +2. What if the cost had been like -2, then you would have said, okay, that will vectorize, but if you had instead done the second thing, it would have been -9. So do you have some way to make sure that you're going to find the optimal?
Right. So with this approach, we are not actually trying so if we have variable width support, we're not gonna try the left-hand side versus the right-hand side graph. So we're not gonna compare them. So what we're gonna do is, while building the graph, like when we reach, let's say, when we reach this point, right, where we have instructions that cannot be combined, at this point here, like, sorry. Yeah, so let me see, because, all right. Okay, so we are building the graph, right? And at this point, we're going to compare whether this approach is better than the left-hand side. So we're comparing whether introducing a shuffle and widening will actually be beneficial for this part of the graph. So consider like only this part. Like we're going to compare this cost against that cost. So it's a localized decision, right? And I think we can rely on the cost model for that.
In some of the performance data you showed, you compared the auto-vectorizer plus SLP to the auto-vectorizer.
Yeah.
And some of those were significant.
Yeah.
Do you have insight into why?
Well, I used the top of trunk. I'm not really sure whether there was any like. I didn't look into that, but you're referring to the first like slide, right? You're referring to this one, right?
Yes.
Yeah.
So something is interesting in the source code, probably.
I haven't looked into why. Like you're talking about the regression here, or like.
No, I'm talking about where it gains, actually.
The gains. It depends, right? So SLP operates on straight line code, and if you have like RGB data or like these are usually instructions one after the other. They're not in a loop, right? So that's the loop vectorizer will miss out on them.
Yeah.
So.
Speaking of RGB, do you sometimes try vector lengths that are not power of 2?
I don't think that's supported currently in the SLP, but yeah, that's a good extension actually. Yeah.
So regarding the previous question, like why there's a big improvement in NAMD? NAMD is like a highly macro. It's a benchmark that's written in macro. Using a lot of macros, and there are lots of straight line code that you can vectorize. And what I found was like, so SLP vectorization, these algorithms are greedy in the sense like, most of the time the decisions are taken at a local level. So I used an ILP solver to like solve and get like, to do this optimally up to a certain vector length. And I found like there are more places that you can improve SLP vectorization. So what do you think about like using explicit packing instructions to pack non-vectorizable code that may be reused multiple times in another vectorizable tree? Like, have you tried a heuristic like that? Like,
I'm not sure I understand your
like
question.
Like say, for instance, if two instructions are not explicitly, which can be, two instructions cannot be vectorized explicitly, but you pack them using like a shuffle or something like that, but later on it can be used in another vectorizable tree, like, or like another DAG.
So you mean if you pack some instructions, whether these are going to be part of another vectorizable tree? I mean, so SLP already supports that. It connects to vector instructions already, so you don't need to add the support for that. So if it finds that some uses, for example, are already vector instructions, it just connects them.
Yeah, but if it's already gathered, sometimes it doesn't like vectorize. Yeah, we could talk offline.
Yeah, right.
Could you go to the last evaluation where you showed the results?
Oops. All right.
So, given that there are like a couple of benchmarks that actually like perform worse in sense that like we get some nice speedups of like let's say 3%, up to 3% here, but also like sometimes slowdowns. What does you make? How do we know that this is not the benchmark selection that gives us a geomean speedup? Because like given 20 benchmarks, we have like a slight speedup geomean, but given 40, it could go down again.
Sure,
so like how do you propose that we can make sure that we don't regress, right? That is the most important part here.
Right, so part of the problem is like the greedy nature of SLP. So SLP has to be fast. So SLP is solving an isomorphism problem, right? So this takes time to compile, and we don't want that, right? So it has to be really, really fast. So each decision that the SLP makes is greedy. So it does not compare. So it could be the case that we vectorize one of the SLP graphs a bit better, but that will harm the next one. So I mean, you need like a global solution to the problem, but that will cost in compilation time. Yes, you can get rid of most of these. Well, as long as the cost model is accurate, you can probably get rid of all these problems as long as you can try multiple alternatives, right?
Do you think the cost model is the problem or the local maximum?
Both, yeah.
Just have one last question about the same performance regressions. Do you think SLP is somehow getting in the way in the regular loop vectorizer for the cases where you actually lost performance? Because you're trying hard to SLP vectorize a block that is actually within a loop, even though the loop might actually be parallel and you might get more vector factor out of that.
Right. So currently, yes, that can be the case. So currently, we run the loop vectorizer first, and then SLP picks up all the remaining stuff, right? Because yes, the loop vectorizer can give you more performance, right? If something is in a loop, it makes sense to loop vectorize it first and then run SLP. Yeah.
Okay, so I got a question about the cost model as well. So how did you design your cost model? How did you validate it? What's the cost of a shuttle?
Question. Anybody has an answer to that? Well, I don't know, like maybe running. Well, I think like a good option would be to have micro benchmarks for everything and automatically generate costs for them. I'm not sure how the current cost model is built, but yeah, like I don't have a good answer for that.
Okay, if you want to, I mean, the current cost model was designed using a mix of a whole bunch of different things.
All right.
So it's mostly based on throughputs. Those throughputs came from some combination of heuristics and people fooling around with vTune on different architectures and some micro benchmarks and a bunch of stuff. I mean, this is definitely an area where we could use some systematic investigation and improvement.
All right, thanks.
I should say the other thing is it's also sort of instruction local, right? So at the IR level, it costs out individual IR instructions and is not very good at costing combinations of instructions yet, which can also cause issues in this context.
Okay, any more question? No? I've got one last question. So I was a bit confused by the name variable width SLP. So I was thinking immediately on ARM's scalable vector extension. So variable width at one time, but this is like variable width at compile time. I would have it suggested maybe to call it mixed width as SLP.
Yeah, good suggestion. I mean, probably a better name would be like variable width SLP graph or something, you know, like because what we're actually proposing is that the graph building process of SLP has variable width. Like SLP already supports variable width to some extent, as long as you reduce the vector factor for the whole graph. But yeah.
So let's thank again the speaker for his great talk.